Hello and welcome to the topic Statistical Tests in the module Statistics. By the end of this topic, you should be able to describe and explain the difference between qualitative and quantitative data, elaborate the basis of parametric and non-parametric tests, recognize the various types of statistical tests used in research. Let's get started. Qualitative data is categorical or nominal data, i.e. the name of things. The only way it can be presented is on a table. No graphs can be drawn. Note that things like gender are qualitative even though numbers could be assigned to them. For example, 0 for males and 1 for females. There are a few questions one must ask when choosing a statistical test. The most important question is, what is being tested? In other words, are we comparing different samples for a point estimate such as mean, median, or frequency counts? If so, this is category 1. Or are we trying to demonstrate associations and relationships? If so, this is category 2. A simple clue is studies looking for causal association will most likely fall under category 2. For category 1, use the following structured approach. Ask yourself, what is the nature of the point estimate one is interested in? Simply mean or proportions? Then, how many groups are being compared? Next, how many observations of similar nature are made in each other? Simply paired or unpaired observations. And finally, can we assume parametric distribution? Is there anything that precludes this? Statistical test mean is a parametric. So you need to ask yourself, is the data not continuous quantitative? Parametric tests can be used if at least one variable is quantitative and normally distributed. Note that most biologic variables are normally distributed. Even if not, they can be transformed into normally distributed values like mentioned. Unless explicitly stated as distribution not known, assume all biological variables are normally distributed for the sake of choosing a statistical test in EMIs or BOFs. When comparing groups, t-tests and ANOVAs are commonly used. Moving on to non-parametric tests, these are used when both dependent and independent variables are qualitative, either nominal or ordinal, or when the variables are quantitative but not normally distributed. In non-parametric tests, ranks, not just medians, are compared. It is possible to have groups with similar means but different ranks. The sign test is a simple non-parametric test comparing the median of a sample to the median of the population. It is the non-parametric equivalent of one sample t-test. Wilcoxon rank sum test is used for comparing two paired observations in non-parametric fashion. This is thus equivalent to paired t-test. Mann-Whitney U-test is used for independent observations in two groups. And finally, Kruskal-Wallis is more or less non-parametric one-way ANOVA equivalent. Now let's move on to chi-square tests. This is a commonly used non-parametric test, especially for comparing frequency count or proportions. A contingency table is constructed when using chi-square test. A table whose contents are in frequencies is called contingency table. When one variable is studied, there are two possible outcomes. If there are two groups, then we can construct a 2x2 table. Observed frequencies are the real outcome observed at the conclusion of a study, while expected frequencies are the outcomes predicted as if the null hypothesis was true. The ratio of observed to expected frequencies in the cells of the table is called chi-square. The rows and columns must be mutually exclusive, i.e. no individual must be represented in more than one cell. A Fisher exact test is used in place of chi-square test if the expected cell frequencies in more than 20% of the cells fall less than 5. In other words, for a 2x2 table, Even if one cell, which constitutes 25%, has expected frequency of less than 5, then corrections must be used. Let's discuss an example. In the 2000s, 48 men were nominated for the Academy Award for Best Director and 9 won. 2 women were nominated with 1 winner. Here, winning or losing is qualitative data. For qualitative data like this, not much analysis can be done, but it is possible to answer the natural question of whether the two different variables are related, i.e., do nominated men win more often than nominated women? This is typically done with a chi-squared test. For a 2x2 data table, which means there are 2 columns and 2 rows, like the one above, it is usual to perform chi-squared with Yates correction. This, of course, is now done by computer. A more exact but computationally difficult alternative is the Fisher exact test. The null hypothesis is that male and female directors that are nominated are equally likely to win, i.e., there's no gender bias. Although women seem more likely to win, as half of the nominated women win, the sample size is small and this result could well have happened by chance. Using the Fisher exact test, the p-value is 0.3667. This is more than 0.05, so the null hypothesis cannot be rejected, and there is not enough evidence to claim a gender bias. Quantitative data is numerical data which can be discrete, taking only certain values like the size of shoes in a shop, or continuous, taking any values like the size of homemade shoes. In parallel trials, one group is given treatment, the other group is a control group. This gives independent data. The natural question is if one group has a higher average value than the other. If the data is normally distributed, a t-test is used. If not normally distributed, a Mann-Whitney U-test is used. Now let's go over another example. 20 doctors are in an unheated hospital and 20 a normal roasting hot hospital. 20 doctors are in an unheated hospital and 20 a normal roasting hot hospital. The number of cups of tea each group takes is normally distributed. What test would be used to determine if the average number of teas drunk is more in the cold hospital? Suppose a few doctors drink an excessive amount of tea. So the data is no longer normally distributed, so it has a positive skew, hence a big tail out of the right-hand side. Now, what tests should be used? In the situation that it is, parametric test includes student's t-test. This could be paired or unpaired, and Pearson's product moment coefficient correlation. Non-parametric tests include Mann-Whitney U-test, which compares ordinal, interval, or ratio scales of unpaired data, Wilcoxon-signed rank test, which compares 2 sets of observations on a single sample, such as a before and after test on the same population following an intervention, chi-squared test, which is used to compare proportions or percentages, for example, comparing the percentage of patients who improve following 2 interventions, and lastly, Spearman-Candle rank correlation. Note that paired data refers to data obtained from a single group of patients, whereas unpaired data comes from 2 different groups. In summary, quantitative data is numerical data which can be discrete or continuous. In the case of independent data, the natural question you should ask yourself is if one group has a higher average value than the other. If it is not normally distributed, a Mann-Whitney U-test is used, but if the data is normally distributed, a t-test is used. For dependent data, it is also called paired data. The natural question is if the group has improved between the 2 measurements. If the data is normally distributed, a paired t-test is used. If it is not normally distributed, the Wilcoxon-signed rank test is used instead. We have reached the end of this topic. Thank you for your time.